Hello guys, this is AM and welcome to the channel. In the past few weeks, we have seen a series of videos on Stack and also have implemented many questions on Stack. From this week, we will be exploring and resolving a good number of questions on a data structure called tree. Tree is actually a subset of a data structure called graphs. Graphs is a huge concept and we will be covering that after trees. Trees are in fact directed graphs. Trees are very widely used data structures in computer science. They have many use cases and are very efficient. Consider the data structure like a real tree. Like a real tree, a data structure also has a root, leaves, branches, etc. So in this, let's explain the terminology first. As I said, like a real tree, it will have a root. Root is a specialized node. The atomic part of a tree is called nodes, and node in itself is another data structure. So it can be an array list, an array, a string, or a simple integer. But it also has another variables which refers to the children of its own. The organization and the collection of nodes makes a tree. To be specific, there are two types of nodes. One is external and internal. External nodes are similar to the leaves of a tree. In fact, in computer science as well, we call external nodes as leaves. A node can be called an internal node if it has at least one child. In this video, we'll start implementing our first tree and see what are the functionalities and operations can be done on a generic on a tree on a generic level. From the next videos, we will be actually implementing many more interview questions related to trees. Make sure you stay tuned and let's start with the video. As we have discussed in the intro, collection of nodes and their organization makes a tree. A node can have multiple children, but our simplicity and for explanation purpose, we will consider that a node will have only two children. This type of a tree and this type of organization of a tree is generally called as binary tree. This is one of the most widely used type of a tree. Let's start the implementation of the tree by creating a node structure. We can create node as a class or a structure itself. Generally, node do not have a function of its own, so we can go with the structure itself. So let's start writing the structure for the node. This is a structure which has three values. One is the data, which is the value of the node itself, but these two are the references to the left and right child in the tree. As we now have our node ready, let's start writing the class for the binary tree data structure. So what about the class methods and the class variables? By default, a tree or any tree in fact will have a special node. This node itself does not have a special structure. This node called as root will be used to access the tree, or it is the starting point of the tree. So we will have our first class member as the root. Root is a class. Root is a structure of type node. What about the methods? We will write down few methods which are most common operations for any tree, like insert. Insert is nothing but inserting a node. Insert node, and bool search or search for a node in a tree. As our node has value of type integer, we will choose the key to be of type integer, and other function like destroying the tree is a functionality which we have to deep delete the nodes one by one. Before we implement these functionalities of the tree, like inserting the node, searching for a node, or destroying the tree itself, we will first see what are the pros and cons of a binary tree by by simply creating the tree manually. By that, without actually writing the functionalities of inserting the node, we can create a tree and see what are the pros and cons of the tree. So we will add a function which returns a dummy tree or a sample tree. It returns a reference to the root of the tree. We will first have to write our constructor. So let's start implementing the sample function. Let's say we have to create a tree something like this nodes. So let's create that. By the way, I'm using JetBrains C Lion IDE. So we will implement 5 nodes. Let's change the variable names, and let's assign the data to the nodes. Let's be simple here. We'll make sure that we are giving unique data value to each of the structures. Now it's time to create the references and point left and right children for the nodes to create the tree structure. So let's call this sample function in the main to see whether we have created the tree in the correct way or not. But before that, we need to return reference of root here, that is n1. Let's create a object. We will have to call sample, which returns a temporary root. So let's test it out by simply calling the roots data. Yeah, as you can see, the tree data structure is manually created. It's not so fancy, but it works. So as we have the tree, let's implement the search functionality for the binary tree and see what its complexity is, and is it really efficient to search for an element in a binary tree or not. Let's ask to create this function. This search functionality we will write recursively. We have to search each and every node for the tree and check whether its data value is equal to the key. Then we can say that we have found the node in the tree. To implement a recursive function, we need to have a base condition. So let's say the base condition is when the root is null, we will return false. So now we will have two cases: if the root's data is equal to the key or not. So if we'll write what if it is equal. So if the key is equal to root's data, then we just need to return true, that it is found. But what if the root's data is not equal to so we simply need to traverse to the left child of the tree recursively and check if its left child is there, and also in the same way we have to see the right child of the same node if it is equal to the key. So for that we need to write So if its left child is not there, we shouldn't do anything, but if it is there, we need to search in the left part of the tree or left part of the root and see if it is true, if left part of the tree returns true or not. If it returns true, that means the node is present in the left side of the node. So we just need to return true in this case. Now we have to see in the right direction if it is not found. So similarly we have to just copy this part and see on the right side. As we have completed implementing the search functionality for our binary tree, let's run it and test it. Our root is temporary root that we have created in this from the sample function. We will try to find, let's say 4, not found. Yes, sounds good, and let's run it and test it. Yes, so the one is from this root data, but ignoring that, element is found. So 4 is found in our sample tree. We have 4. So as we have so our search functionality is working. But so as you see, we need to traverse each and every node of the tree in a worst case scenario. This is bad. So we could have just used an array, right? But there should be something that makes it unique and more efficient than arrays. So here BST, that is binary search tree, comes to the rescue, which actually drastically changes the search time. What makes binary search tree different from a normal binary tree? As the name suggests, binary search tree is very similar to binary tree. That is, the number of children a node can have is 2, yes, but it also employs a simple rule which makes all the difference. Binary search tree says that while inserting a node, do not insert blindly. The rule to insert a node in a binary tree is a node can have a left child which is lesser than the value of the node itself, and the right child should have a greater value than the node itself. Sounds tricky? No, not at all. We will explore more about the binary search tree, and actually we will stop implementing the binary tree, rather implement binary search tree and also various other functionalities that we have written in our class, like insert node and destroy tree, etc. can be written from binary search tree. That makes sense because binary search tree is far more superior than a normal binary tree. And I'll see you in the next one.